Hey guys, it's Edward. So today I want to show you what it takes to work through a complex code base that you are unfamiliar with, find the bugs that are relevant to you, and submit a pull request in open source software. While each of these can be an entire video in and of itself, I thought I would actually give you a solid example of me executing all this together. I'm going to show you how I open sourced one of my diffs and show you how I debugged the bug behind it. I'm going to structure this video as more of a story that hopefully highlights how I think about complex problems. I will also give optional side analysis throughout the entire video that will help you figure out why I am making various decisions in my problem solving. These analyses aren't necessary to the story, but they will help you become a better developer because they will go into the logic of why I make certain decisions that I do. Don't worry if you don't get the answers right away or if you don't completely follow what is going on. This problem took me a full month to debug and fully figure out. So with that, let's begin. So let's start at the beginning. I'm trying to build our code base using the Bazel build system, and occasionally I will see this very annoying crash when running our builds. This is pretty bad. After all, nobody wants to have their code randomly fail compilation for an error outside of their control. If we wrote some bad code, fine, but this error occurs even if we are working on a good code base. So naturally, our objective here is to find the root cause of this error and eliminate it. I want to point out that this particular assignment isn't unlike the standard bugs junior engineers have, except for the fact that the cause could be in either one of two multi-million line code bases. Now, why might I say that the problem is in two code bases, not one? Let's define what exactly a build system is first. We often forget that there is some complicated piece of software, some code or build system behind our IDE that compiles our code base. When we push compile on our IDE, a call is made to the build system in order to execute a bunch of compile commands in order. Now, keep in mind that build system is code and has its own code base. Therefore, the problem or bug resides in either our code base or the Bazel code base that's actually building our code base. Maybe our code is written incorrectly and our previous build system passed it for absolutely no good reason. Or maybe the way that these compile commands is run is incorrect in and of itself. So it's basically an L3 bug fixing task expanded to a very large degree. It's not just a couple classes in a package, it's any line in a couple million lines that can be problematic. Literally, a needle in a needle stack. Fun times. Now the astute viewer might say,
Wait, obviously it must be in the Bazel codebase. After all, your code is compiling just fine.
I'm going to do a little bit of hand waving here, but suffice it to say that the old build system that we were on and that did the original compilation does a lot of things incorrectly and compiles code in a very odd way that somehow works out in the end. So going into the problem, I didn't fully 100% trust it. In fact, it's one of the reasons why we're migrating off this build system. But for the sake of this video, I'll just kind of hand wave that discussion. Next, let's look at what kind of solution we want. After all, if the issue was as simple as running out of memory or something, we could just throw more machines and hardware at the problem. We could just add more RAM, or we can replace the CPU, or give everyone new laptops. But this would be very expensive and very stupid. People think that just hiding the error is fine. But we want to solve a problem as permanently as possible without having to revisit it. In the worst case scenario, let's just suppose I'm only covering the symptoms, not the root cause. If the root cause can cause other compilation problems in another module or might be problematic in another part of the code base, in the Bazel code base specifically, then I really need to deal with it. And at that point, I'll have eliminated some information just simply by suppressing the error. That will mess up my ability to really solve it properly in the future. I want to make sure that I never see the stupid bug ever again. This is a high priority bug because we are never going to want a developer to compile their code and for it to fail for reasons outside of their control. In general, a fix is valued based on these 5 traits: the ability to implement it easily, the ability to maintain it easily, to show clear measurable progress, has high impact, and is scalable. The more boxes we check off on this, the better. Let's consider why we want to have all these though. Skip to this timestamp if you want to skip the boring technical details. Not only do we need the fix to get us around the problem, we need to maintain the fix as well. We don't want to have to regress or have a fragile fix. That will mean revisiting the problem. The build system and codebase needs to be extremely stable since it will be used by hundreds of developers and run thousands of times per day. What happens when the codebase changes? Or what happens when the Bazel build system codebase changes as well? Will our fix still work? Can we even update the fix if it's needed? If it's overcomplicated, then chances are we will have to do a lot more merge conflict resolutions than we otherwise would have. We don't want to overcomplicate things by forking a build unnecessarily. Forking means we will submit fixes that have no oversight or review, meaning we do not know if 100% if these fixes are right or not. They may conflict with the maintainer's future plans for the codebase, and we will have to try and figure out these things ourselves. In some cases, we may need to do this, but only when we have no other option. We also need to show that we're making progress with the fix. That is, how do we know that we're not slowing down the build in other ways just to fix this? How do we know we're not causing a regression? Maybe the bug was an accidental consequence of a patch, and undoing the patch to fix the crash will bring back the original problem. Finally, we want to know if the price we pay, if any, in terms of performance or maintainability is worth it. Nothing comes for free. The progress we make needs to be measurable. We already know the system works quite well, and we are at the mature stage of the software lifecycle with Bazel, where every fix needs to be deliberate and have a very obvious net benefit. After all, Bazel is the code build system that Google actually uses internally. So we can assume, for all intents and purposes, that it was deliberate and very well maintained. We cannot just submit hacks after hacks that will kill our performance. That would be product suicide, essentially. Also, we would have a lot of angry developers complaining about build speeds. So pro tip, before you write any fix, know why it is the best of all possible fixes you can have and understand why it works. When diving into a problem space, I very often just start with what I know and the potentially easy fixes. If I can get that, it gives me direction and it helps me eliminate possibilities very quickly. First, start with the existing literature. Some simple Googling will suffice here. I find an existing ticket with the exact same crash stack that I am encountering, and I even find a tangential ticket that seems to address a similar issue with decent explanation. This isn't the same codebase or issue, but it seems very similar. Let's go with this for now and assume that the core cause is exactly the same as our working hypothesis. Looking at the existing literature, namely this Stack Overflow answer, and combined with the filed TensorFlow ticket, in all these posts, it looks like the most likely culprit is some kind of out-of-memory killer triggered by the operating system. Most operating systems come with a mechanism that prevents issues by stopping and killing programs that use too much memory. And it turns out, Bazel is getting consistently killed here because it consumes too much memory. This makes sense, but there may be other possibilities here that I did not consider. I might be biased towards the first answer I see. To avoid any biases, I always look for contradicting evidence and data points. This is where I go to the second step in my troubleshooting. I'll do this by reproducing the bug under various conditions in order to eliminate all the extraneous and unrelated factors to reproducing it. I will try to build my code over and over again on different machines, different versions of the code base, and under various loads. This will give me more data points and scenarios to test against, and more insight into what exactly is causing the issue in case I want to debug this in the future or go any further. Now I'm going to go in depth a little bit. Skip to this timestamp if you want to skip this discussion. I want to highly emphasize the use of contradictions and anomalies when troubleshooting your code. Why? In engineering, it is very easy to misinterpret and misunderstand things. Our minds fill in facts for us based on preconceived biases and our past experience. The longer this misunderstanding stays entrenched in our heads, the more it will deceive us and prevent us from actually getting to the correct solution. Therefore, it is very important for us to distrust anything that might seem like out of the ordinary or if it contradicts our initial understanding of the problem. It is one thing to think that a solution is correct. It's another thing to prove it. Let me give you the 5 observations I noticed about the out-of-memory condition when running through this. I'll put them on the screen. Now I want you to arrange these from most suspect to least suspect. Pause here if you need some time to figure it out. Alright, cool. Here's the order. Well, why is this the case? Well, it's very obvious why the first one is here. This is because we are facing a fundamental contradiction. It's not surprising if someone making below minimum wage is living paycheck to paycheck. But if someone is making a lot of money and living paycheck to paycheck, you'd be giving a big eyebrow raise. Same here with memory. How is it that a crash can occur out of memory when we throw even more memory at it? Next is the reproducible when we clean the build and restart from scratch. I rate this one second because any system in general will reproduce the same error over and over again if you start from scratch over and over again. But usually, most bugs only manifest when you use the system long enough. This is one of those rare instances where a bug shows up in the actual beginning of the run. This is also a great leverage point because it means that we have an easy deterministic way of reproducing the bug we want. Here's the third one. Out of memory sometimes occurs late in the build. This is fairly obvious because as we throw multiple compile commands, we are going to be building more and more binaries and apps. Each of these binaries will feed as inputs to other binaries and other compile commands, similar to how a Java jar can be used as an input to compile another jar. In the worst case scenario, these jars are just copied from one another and have a supermassive jar at the end. Of course, this is an oversimplified version of the reality of things, but you understand the point. The more operations we have, the more room for error, and the bigger the final binary may be. By this logic, we must also rate this one as less suspect, but it must be more suspect than this one. Hopefully this explains my decision making when deciding which clues to chase. Having tried building under various circumstances, the first interesting data point is that the bug almost always happens towards the end of the build. Okay, fair enough, this kind of makes sense. The second data point is that there is a significantly higher frequency of the crash on our remote execution environment. At big tech companies, because of how big our codebase is, we may want to use server machines in order to run and build our systems. These are called remote execution environments where we upload a branch or some code and have the big server build the code for us. What's the contradiction here? The contradiction here is how can we constantly be running out of memory if our local machines, which are far inferior in memory to our remote execution, is able to complete builds and our remote machines aren't? And what about the end of the build causes this to happen? Because this contradiction is so weird, I'm going to keep this one at the forefront of my mind. This is going to be the key to solving the problem later on. The third data point here is that I find that if I run the build command over and over again, it will eventually complete and generate the compiled binary I want. But this is a terrible developer experience, and a lot of people will be running into this issue. I'd rather not subject people to ramming their compile commands until their code compiles. Still, there are not enough points here to tell me what exactly the issue is, but these are going to be my north compass. Looking closer at the logs, I noticed that we tend to frequently fail compilation on two steps: Kotlin compile and dexing, which occurs later on in the build. Now, let's clarify something. Dexing is a bytecode operation, some post-compilation tasks, if you will, that can be run after all the Java and Kotlin code has been compiled. And Kotlin here is just a language, so you can think of it as a language compile. Now, with all these data points, I can begin to narrow down the issue. Fortunately, the most suspect data points gives me a game plan: clean and run builds on a remote execution machine and not our local environment. When I try to come up with initial solutions, I always aim to exhaust all the easy ones, the ones that are easy to implement and are likely to work, even though they may impact other areas that I don't want them to. From there, I can at least tell that I am on the right track and there is something in the solution that will work. Think of it like your naive solution when you go and try to do your data structures and algorithms interview. All you really need to do is get something on the table that actually works, and then you can make it more efficient. I'm doing exactly the same thing here. Based on the data points, I know that it must be a memory configuration that is specific to my big resource machine. So I look at the fundamental ideas in Bazel that are easily modifiable via a config value or something similar, maybe a documented flag. There are three things here that can be the culprit. The first one is that there are too many compile and post-compile jobs that we run in parallel. When we compile things, we will give these jobs to workers. In this case, a job just represents one unit of compilation. So effectively what I'm saying here is that maybe we are running too many jobs at once. The second here is the number of compile tasks that we run sequentially per process. This means that we lower the compile time of Java by not repeatedly freeing up and consuming the virtual machines that Java needs. We will call this the number of multiplex workers. You can think of this as essentially a worker gets a job and then usually has to spin up and then shut down once the job is done. The multiplex worker in this case can keep consuming compiled jobs over and over again without having to shut down. In this case, you never have to restart or stop the Java virtual machine. The third here is the strategy we use to compile each step. It could be a remote compile where we compile it on a cloud machine, or it could be a local compile strategy that we use to compile on the laptop itself. Now, based on our criteria of what makes a good fix, which one of these would I want to have as my final solution, and why? I'll put these on the screen for your convenience. Well, actually, it's in the order I presented. The first one here would be too many compile and post-compile jobs process we run in parallel. This makes sense and is the simplest. After all, just overall limit the number of processes we're running. Simple and easy to tune. It is the easiest to test for as well. Make sure that a job that usually doesn't compile well compiles. So it is the easiest to maintain. It's scalable in the sense that it applies across the board as well. But it can also be its own undoing if we find that we pay too high a price in compile time. The next one, the number of compile tasks we run sequentially per process. This one is pretty complex. While it's easy to implement, it's much harder to maintain. After all, how could you test to see if the virtual machine is really being restarted or not? It is also harder to understand and explain to someone else than the first solution. I would also posit that even if this was the culprit, I'd rather not modify this since with the thousands of jobs we run, any compile time savings that we get across of the same type of job is massive. The payoff here is too small. To illustrate this, think of having 1,000 Java compilation jobs. Each time we start and stop a job, we have to spend time spinning up the Java virtual machine and shutting down the Java virtual machine. When instead, we could just compile all these back to back without ever having to take that friction cost, we would get a lot of savings. The last one here, the strategy we use to compile each step. It could be a remote compile, it could be whatever. Similar to number two, this is even more complex compared to fine-tuning just well a number. Complexity tends to go hand in hand with the amount of effort I would need to implement, test, and maintain it. The payoff here is much, much smaller, but I'm going to keep this one in the back of my mind. So let's try the first solution. Try to limit the jobs. This really doesn't quite work. I first overly restrict the jobs and the workers to save the most amount of time. Only one worker makes our builds painfully slow and took an hour and a half to finish a build. This is really unacceptable. This fails the measurable progress test. We're actually regressing in build quality. But we at least know that there is something here that works. I tried 3 workers. 2 workers fails on the later dexing task primarily, but 3 fails on Kotlin compilation during the middle of the build. And these numbers really work, but this does give me a hint that dexing does consume far more memory than Kotlin. The next one, I tried the multiplex workers. This really doesn't change anything either. Changing it doesn't really cause a change in behavior, so I think I can safely rule that out. Finally, I thought about the strategy's manipulation. This was way too complicated to investigate, so I left it alone. It doesn't seem directly related to my issue, and it's not clear to me how this in any way would be beneficial to explore. I'm going to table this for now. I like having this idea of a too hard pile, actually. It forces me to travel down the lane of knowledge that I do know before I tackle the too hard stuff. As engineers, we naturally like to solve things. So it's our natural instinct to see a sign that says danger, danger, do not enter, and just enter it, thinking that we can solve it or that the guy putting it up was an idiot. Simply respecting this lazy instinct of mine allows me to work on a much more efficient level when it comes to solving problems, simply by avoiding the really difficult ones. So none of these were really viable, but I got a few data points, namely that there is something in the number of jobs or some fact that is related to it that is causing the issue. Let's look at how these jobs are actually being run and assigned. Perhaps there's something faulty with my own understanding. Essentially, we need more research. We need to dive into why this job limitation works. I know that there is something in the number of jobs that is causing the issue, but I need a more fine-grained solution. This is where we want to refer to the documentation in Bazel. The short version here is that there are 3 phases: the loading phase, the analysis phase, and the execution phase. The loading phase just parses all the Bazel specific files. The analysis phase figures out what job to execute and how, and the execution phase is the actual compilation that the build system fires off. So all that's left to figure out is which section of code the documentation latches onto. I'm going through the code base and putting breakpoints where I think the issue may occur. I want to catch the point where jobs are being assigned to workers and begin to understand step by step what exactly is happening inside the Bazel codebase. As I dive into what creates the number of workers and jobs, I notice that there are extremely limited by the CPU analysis. That is, we spin up the number of workers as we have threads. So there is some kind of classification with each one of these jobs and whenever we run the analysis on them. So what are the troublesome Kotlin compile and dexing jobs classified as? Well, heavy CPU. That naming is really interesting. So what happens if we limit both the number of workers and artificially restrict the number of heavy CPU jobs? This chokes our analysis phase and our dexing operations. That is, by limiting the heavy CPU labeled jobs, we're forced to limit every other operation that is also labeled heavy CPU. So our analysis time just gets completely destroyed, our build time gets completely destroyed, but we are at least able to actually finish compilation. despite the builds being insanely slow. Furthermore, the fix for this would be relatively unmaintainable because while this flag, I'm going to put it on the screen because it's way too long to say, is very experimental. It's still very likely that Bazel can take away this in future versions, and it's not even documented. In essence, we can think of this as a slight hack, which violates one of the principles that we set forth for a fix to be a good fix. But we at least have part of a solution. We know that some combination of limiting workers and a thread pool management will get us somewhere. Now, I want you to keep this fix in mind, that we can artificially restrict the number of jobs that are specifically labeled heavy, because we will do some compare and contrast with it later on. Now, how should we use this fix? At this point, I've burned a week of my time. It is at this point I take note of whether or not I want to continue troubleshooting this or not. This is a strategy called time boxing. I limit the amount of time I spend on a task to ask myself if I should keep going based on the payoff scenarios. In engineering, it's not important whether I'm right or wrong. What matters is the answer is good enough for the amount of effort and risk I am expending. If I think that a potential answer is likely good and is good quality, especially compared to what I have currently, then I may want to invest a certain amount of my time. The amount I invest is proportional to the effort and risk. So the lower quality the potential answer to my current state is, or the less likely I'll get to an answer, the less amount of time I'll spend on the task and vice versa. Applying this framework here, the question is whether or not I should continue to pursue a better fix. First, let's start with the state I am in. I have a fix, but it slows down our build times dramatically. It's obvious that insanely slow build times are a bad thing, but am I willing to pay the cost of having a temporarily slow build in exchange for getting past this hurdle? Maybe there are more pressing issues that I have to get to, and this is just a good enough band-aid. I would say that the answer is no. Nobody in their right mind would accept a 100% build time increase on a long-term basis even, especially since it takes 10 minutes to build our code base already. While we might accept it temporarily, and barely if that, we don't want it in the long run. Plus, if I want to explore other bugs in the Bazel codebase, having an extremely slow build here just completely destroys my momentum, and it takes much longer for me to try and debug any other issues. In other words, the future fixes that I may want to work on are dependent on this fix being efficient and good. To think of it from another angle, let's think about the rewards. We reap dividends in the long run, having actually solved this issue as these build times are run several times a day. There's also a pretty good payoff for pursuing this fix, namely having a community-wide impact. Based on the initial research I did, I suspect that the community will encounter this again and again, so this will save other people out there lots of time. Not to mention, we will have to deal with this eventually, so why not deal with it now instead of later? That sounds great as the reward side of the equation, but what about the downside? That is, what happens if we fail, or what is the risk we are taking on? If we cannot make progress, we will just fall back to our current backout solution, the heavy tasks plus jobs. While it's agonizing, it at least gets us over our hurdle and we can continue working on these things. I want to point out something here. The fact that we have a backout solution actually changes the expected value equation. Assuming binary events, expected value is defined as the payoff in event 1 times the probability of event 1 happening, plus the payoff of not event 1 happening times the probability of not event 1 happening. So if our event is me actually finding a solution, then we have a higher expected value simply because I have a temporary solution ready to go. This temporary solution is worth more than having no solution. Had I not had a backup solution, I may have reconsidered, but this calculus shows me that we are right in pursuing a better fix. I will give myself another week and reevaluate after that. Pursuing the fix and thinking about what makes the heavy CPU limitation and number of jobs work, I am convinced that if we limit the memory and CPU that Bazel uses in a different way, we can actually fix all our issues. So let's actually find that better fallback solution. The fact that this naive solution works means that I have the data point that limiting memory will give me a solution. The most immediate option that comes to mind is that we can just limit Java memory itself. Bazel is fundamentally a Java program, and all Java programs respect the parameters of the JVM. So if I limit the JVM memory itself, then it should be just fine. I can limit the JVM's consumption for Bazel with the XMX parameter with some arbitrary number in the config file. I run a few builds with a few different values of XMX using the binary search method, and we can actually reduce this parameter down to about 16 gigabytes. Our build passes, but we incur a 20% increase in build time, which is much better than the 100% increase in build time that we had before. This will be our second fix to restrict the Java memory to 16 gigabytes. Compared to our first fix, it is a little better. It's not super experimental where we are messing around with the guts of Bazel or with some experimental API. It's still a general shotgun approach in the sense that we are still limiting every activity because of one glaring issue. But the penalty for using this approach is much less than what we had earlier. So let's actually check to see if this is a good solution. Is it easy to implement? Yes. It's a one-liner. Is this easy to maintain? Yes. We can tune the number itself. Have we shown clear and measurable progress? Well, kind of. It is a bit weak on the third criteria. The reason? Because while we do make progress by getting around a crash, we are accepting to take on a different trade-off in terms of build speed. We don't even know what the real root cause is. All we're doing is hiding the symptoms. We are effectively kicking the can down the curb, like I mentioned earlier. But does this have high impact? Yes, this works and can solve a multitude of other potential issues and scenarios, and can actually be used in other bugs as well. And is this scalable? Well, not really, because we impact a bunch of other scenarios negatively. Let's do another litmus test. Why else might this be a fragile solution? Let's try to beat the crap out of it and prove to ourselves that the solution isn't as clear or robust as it seems. Why are we able to complete the build for some values of XMX and not for others? MacBooks have 64 gigabytes and the build is fine. Remote cloud builds have 96 gigabytes and fail. These are all Java and Kotlin processes as well. If memory is a problem, I would expect garbage collection to kick in and free up all the memory. There's no way that we could consume all 96 gigabytes ourselves, and limiting Bazel to 16 gigabytes is enough. But what happens to the other 80 that's out there? Remember that point from earlier that we tend to get this issue more when we have larger, more powerful machines? Limiting Java's memory does not adequately explain or cover this phenomena. Usually, we can punt that discussion as long as the fix is permanent. But the fact that it is not and is subject to change in the future is kind of forcing our hand. In other words, we are likely to face this again down the road. We don't know the exact cause, but if it's related to the number of jobs and workers we have, this is a variable factor that may ask us to revisit the solution down the road. For instance, will we have to change the amount of memory Java uses again to an even lower amount as our codebase grows? So yes, this solution does check off the boxes for a good solution, but we can do much better, especially since the threat of revisiting the fix looms overhead. Going back to the drawing board, let's list our facts and points of interest. We know it has to be the way Bazel handles actions and consumes memory. We know that the dexing operation is a big culprit because it is classified as a heavy CPU task. We know that the workers and multiplex workers do contribute to the issue, but the bottom line is the dexing operation that seems to be giving us grief and is not controllable by the default parameters. We still haven't figured out why this problem occurs more often on remote cloud machines that provide more resources to the user. These machines have a physical memory of 96 gigabytes, yet we're stuck limiting the user to 16 gigabytes whenever they run Bazel. We have tried every obvious documented solution and option without much success. We have a base solution that kind of works that limits Java overall. While it works, we don't understand why it works in relation to Bazel specifically, and any idiot can constrict resources and call it a day. Ironically, it is this last fact here, the fact that we have solutions that we don't fully understand, that is actually the only actionable fact here. We don't fully understand what part of Bazel is using a lot of memory that necessitates this memory limitation. We know that it is likely due to Kotlin or dexing operations, but so what? What about these operations make them special? Not to mention, if we think about limiting all the memory, why is it that we need to limit Java to 16 gigabytes? Why not 17? Why not 25? So let's dig into the memory usage. What makes Kotlin and dexing so special? To handle these two issues, I'm going to sample the machine's memory. That way, I can see how much memory each process is consuming right before we crash and get killed by the out-of-memory killer. Maybe these processes are doing something that I'm not aware of and are actively ignoring the Java limitations. I found a tool to do this for me, and after spending a day modifying this bash script, I was ready to go. This script will just traverse through all the running processes on the machine. Then for each process, it will do a lookup of the used memory. It outputs them to a CSV file where I can just rearrange the data and sort it by size. What I added was the parent PID who owned the process and a way for me to distinguish between physical and virtual memory. The reason why was because out of all the processes that may be running on my machine, I wasn't sure which processes were tied to Bazel and which weren't. While this was good bookkeeping, It proved to be unnecessary later on, but 90% of what was used is in the script. This isn't exactly foolproof because there is a time delay between each lookup and the retrieval of the memory information. So there may be some processes that have died and don't have its information available to us, but we can still get a roughly good idea of what's going on. I just spam the build tool while Bazel is running over and over again, especially when it gets closer towards the Kotlin and indexing operations. Looking at the data, I notice a lot of anomalies in the data. Why are there so many Java commands coming from Bazel? Why does it consume so much? It deliberately ignored the 16 gigabyte limit. We can easily see that the number of Kotlin processes match up with the number of workers we've assigned here to Kotlin, but the memory usage here is awfully high. One way to fix this is to limit the amount of memory Kotlin actions themselves are using by passing the XMS parameter to all Kotlin actions. Kotlin uses the same Java virtual machine that Java uses, so it should accept the same parameters. I spent a day trying to figure out how to pass the XMS parameters to each of the Kotlin actions, but suffice it to say, it was extremely difficult to do right out of the box. The reason is that when you run Bazel, you specify a toolchain or the version of the programming language you want. Then Bazel will actually download that programming language binary per the toolchain and run all the commands using that downloaded version of the programming language. That's right, the version Bazel uses to run Java commands to compile and the version that you have installed on your machine to run Bazel itself are two different versions of the language. So whatever arguments you are passing into the JVM only apply to the version of Java that is running on your machine, not the version of Java that Bazel is running. Pretty confusing, right? Per my time box strategy, I decided that because there are far more promising routes, we can come back to this later. So for now, let's call this a dead end. So okay, we cannot control the Kotlin memory usage. What about our bytecode dexing operations then? Looking at more samples, I see that there is this busybox operation that gets run with very high memory as well. Busybox is a Java program as well and should have gotten the same XMS parameters as well. Yet clearly it doesn't. So I'm going to skip trying to pass the XMS argument as busybox as well, because I imagine it will be just as difficult as passing it to Kotlin. But more importantly, I see that there are a lot of actions that are running during dexing that violates my job parameter that I've set. How can there be 17 dexing actions running if I have only set 8 in my configuration? It is at this point that the world makes less and less sense to me. My understanding of how Bazel works and how these systems work is in direct contradiction to what I am seeing. We have more and more contradictions the deeper we go, and fewer options to deal with them. It's a huge mess. Why is it that Bazel is repeatedly ignoring these flags that I'm setting? Flags that are explicitly documented to work. It is very unlikely that in a mature codebase like Bazel that there will be multiple bugs affecting this, or that it was improperly tested. It is at this point I usually look for commonalities in these contradictions. Given all these contradictions in what I know, there must be a single underlying issue or group of issues that must be connecting all of them. There must be one single fact that is causing Bazel to not do what is being documented. Either the documentation is out of date or there is a single major bug. Usually, I'm leaning towards the latter. So, analysis time. When you access your pool of facts, one of the best approaches is to find one or two commonalities between all of them. After all, in this project, there are thousands of areas I could dive into. I could circle back to the heavy CPU solution. I could dive into the Java virtual machine and compiler as well. I could even look at the job scheduling. But most importantly, I need to look at the Bazel code itself. But what area should I look in? I've already looked in the analysis phase, so do I need to start over? Let's list our headaches and points of interest. I want to show you an interesting trick on how to evaluate what assumptions you may or may not be making. So here's all the things I mentioned before. We're likely to encounter this on a machine with more memory. We are spawning more jobs than our configuration allows. Many of the subprocesses and jobs regularly exceed the memory limits that are explicitly placed on Bazel. The jobs that are spun up are ignoring our memory limitations. We are repeatedly seeing the documentation contradict the behavior with regards to jobs. What is the common theme here? Yes, it's memory, but what specifically? I would argue that it is the way that Bazel is scheduling and running these jobs and compile commands. How does Bazel know when to spin up the next job? Is there some bookkeeping that it does wrong? The rest of the points, such as Java compilation and Java analysis, don't seem to apply here. Sure, maybe there's something wrong in how Bazel does the analysis and scheduling of the tests, but I will need to make that secondary. For now, it is very obvious that we need to debug the memory bookkeeping. So, how did I figure this out? all I really did was just trace up the chain of dependencies. So instead of going all the way to the root and saying that it is an issue in the operating system itself or saying it's an issue in the Java virtual machine, all I did was look further and further down and say, hey, that it must be something in Bazel itself, something memory related in Bazel. After all, that's the next node up from everything that I've been doing. Now, this is an abstract idea, of course. There's many, many layers to this, and there's many different levels that you can go to, and how deep you want to go is based on your experience in debugging these things. But for me, I almost always just start with the issues in front of me and then work my way up layer by layer by layer until they all converge. So my best option now is to get a better understanding of resource allocation in Bazel, or rather how Bazel chooses what actions to run, because none of this makes sense, and this is the linchpin to all the issues. At this point, I'm 2 weeks into my investigation. I decide that it is worth spending an extra few days on. I re-examine my payoff solutions, and I am reasonably confident that I can come up with an answer and a good fix in 1 more week. At best, we solve the problem and move on. At worst, we come up with more knowledge on how Bazel works under the hood. Almost always, if there is a component that is critical, widely used, and poorly understood, spending time to understand it is usually a very, very good decision. This calculus and principle has not changed, and by debugging this far, we have learned a lot about how Bazel operates. So this has given us good fruit so far, and I think that we can get much more going forward. And I get a feeling that we are very, very close to the finish line. We have one single task: understand how Bazel allocates resources. We know that our issue must be there, and with a very narrow question, we can now just repeat the exact same tactics that we used at the beginning. First, let's look at the existing literature. And just my luck, I found a blog post by a formal technical lead on the Bazel project and with a few relevant tickets. In this blog post, he pretty much lays out the whole roadmap for me. The short version is that there is a resource manager that calculates how much resources every action will consume. It is then responsible for spinning up actions and jobs. It will add jobs to workers based on resources needs per job versus how much it is allowed to consume, or if no limit is placed, how much the system has provided. Perfect. This means that either one of these dimensions are wrong, either the calculations for the amount of memory the system holds itself, or the calculations for the estimates of the memory per process. Or in the worst case scenario, they're both wrong. So let's confirm this by running a few commands, namely the dexing and compile command. Unfortunately, because the number of threads and things are flying around, I wasn't really actually able to use a debugger. So I start logging the hell out of the Bazel codebase, logging where Bazel gets the system memory, logging where Bazel spins up and retires a job, every entry point that can affect Bazel's memory calculations. I like to point out that a lot of these tools and debugging skills are skills that you learn pretty early on in your junior developer career. Even the newbie approach of just print everything is still useful from time to time. Looking through the logs, we actually get our answer. This is actually going to be a little bit technical, but bear with me. First of all, the amount of memory that Bazel thinks it has access to is terribly wrong. We are severely underestimating the amount of resources each command is using. The source of truth is in this procmem information file that's in Linux, but by default, our remote machines are shared and those get put into C group. What this might mean is that let's say we have a 400 gigabyte physical machine, but it has 4 containers. That means that each container is allocated 100 gigabytes, and each user is allocated 1 container. But Bazel sees the 400 gigabyte available to it on the hardware side and thinks it's available because that's exactly what this source file is saying. But some of you astute viewers out there might say,
Oh, wait, modern operating systems have virtual memory. So, in theory, operating systems could spin up a lot of swap memory and absorb all this and prevent this from actually crashing our system.
aha, good point. But in the same system report that I checked out, I noticed that we actually have zero swap memory. This means that we have 0 pages that can absorb this, and turns out the remote machines have none at all. This means that we have no additional memory to fall back on or to create on the disk, and so we will crash whenever we exceed that limit. Because the operating system has no more physical memory, it must start killing off processes, in which Bazel is the first one out. Perfect. This absolutely explains the biggest contradiction about larger machines running into out of memory more frequently. On larger machines, we assume that all the memory belongs to us when that number is way off and we have no swap to fall back on. Kind of like overspending an income we vastly overestimate with no savings in the bank. This brings us to a second observed issue: the estimations that we make versus the data that I sampled. Remember the tool that I wrote before to dump the memory? This is where it actually begins to come in handy. I see that Kotlin takes 2 gigabytes of memory in my data, but Bazel estimates it to be actually 250 megabytes, which presents a very big problem. In short, if we say that we run at most 8 actions, and where Bazel has 10 gigabytes free, Bazel will spin up all 8 Kotlin actions. But because Kotlin actions take up 2 gigabytes, we may end up in a situation where 16 gigabytes are actually consumed. With no swap memory to fall back on, out of memory gets run and we crash. This is why limiting our number of workers has worked before. Remember our first solution, the heavy CPU limitation plus the number of jobs? Well, if we limit the number of jobs, we already indirectly limit the memory we use. This explanation perfectly fits into our previous naive solution. At this point, the pieces and everything have fallen into place. There may be other factors at play here, but for now, I am satisfied with this. So, how can we tackle all of this in an elegant solution? Technically, there are 2 problems. The first is the miscalculation of resources because Bazel overestimates the amount of memory available to it. The problem exists because of Kubernetes, the software that is responsible for managing these containers. On a single physical machine, the resources are divided amongst the containers. But the Bazel program is running in the container, thinks all the physical resources are available to it and it alone. Solving this in Bazel is not easy. This requires a complex architectural change and requires a lot of involvement from Google. Most of you think that it is just as simple as creating an interface and then labeling the source as Kubernetes or not Kubernetes, except that there are many places in the codebase that assumes that the source of truth is a file and not done through a class. I don't know how many other places are incorrectly assuming this. After all, how many programmers would know about that little nuance in Kubernetes? Most people assume the fidelity of the operating system and whatever is documented in Linux. And it's a fair assumption to be fair. In general, the open source software attitude is that the managing authors don't like large community overhauls. Changes to architecture is generally just that, and any fundamental shift in refactoring or reorganizing code is going to incur a lot of scrutiny, not just from the Google maintainers here, but also other developers at large. So I'm going to avoid this one because the problem here is too hard. Again, the too hard heuristic here is going to do wonders for us. The second problem is properly estimating resources per job. We want to give the user more fine-tuned control over how much resources are being consumed. This way, users can overestimate certain actions if they think they're causing them grief. This is very easy to do. I'm going to just inject this parameter as an override into the resource manager. I'm going to pass it through a few layers of indirection. This is a bit ugly and not elegant, but it will hold me over. So, after all that, with a month of my time lost and many wrong turns, I have a simple, elegant fix that neatly solves many of my issues. My glorious small diff and small change that can relieve many people across the world of a world of pain. It is ready to be merged in. I pushed this up to GitHub and I'll link it in the description down below. Hopefully the maintainers can see its merits and all the explanation that I've made and okay, this is a bit of a long video and this warrants a few rewatches. But here are the top takeaways that I think are going to absolutely be useful to you guys, no matter what part of your engineering career you're in. First, think in terms of payoffs and values, not in terms of what is right or wrong or what will happen and what won't happen. Notice that several times I had to really prioritize which issues to take seriously and which ones not to. Should I pursue a better fix or not? All depends on your likelihood of success and what the rewards will be in each one of the scenarios. Your time is valuable and you cannot solve every problem perfectly, but you need to be able to solve a problem efficiently and come up with a reasonable solution in a reasonable amount of time. Knowing the right payoffs comes through experience, and the more aware you are of where you spend your time, why you are spending your time in which places, and what the results are through various trials and errors will make you a better developer. This leads me to the second point. Free wins are the best wins. This is where research and study can save you a lot of time. I would not have had the justification to pursue the fix if I didn't do my research in other similar areas and tangential issues outside of my immediate use case. I would not have found the roadmap to the finish line had I not found Julio's blog. While the documentation may be unreliable and some of the issues can give you hints instead of full-on answers, those learnings are still free and small, and you should be able to take those whenever you can, and they will help you make better decisions. As a side note, I would highly recommend that you write down your thought process and attempts as you progress. This will allow you to have a record looking back on when you need to remind yourself of what you've tried and what you haven't. It also acts as a rubber ducky where you'll find that simply being able to explain the problem will also help you solve it. I find this extremely helpful myself, especially with lots of screenshots of the stack trace, because honestly, my memory is pretty crap. Third, contradictions are a great hint. Every time that there is a confusion or contradiction, there is a learning moment, or in this case, multiple ones. Whenever I got stuck, I looked for a contradiction or multiple contradictions to guide me. We repeatedly had the contradiction where a bigger machine was more prone to out-of-memory failures, and the key paid off in dividends many, many times in progressing through the problem. Contradictions and confusion don't have to be about your knowledge. They can also be related to the environment it exists in, or in this case, the code in which it works on. Being able to iron out these and provide a good explanation of why they exist or why you were wrong pays dividends in the long run. Because most people do not get stuck because of a lack of knowledge. Most people get stuck because of something that they assumed to be true that wasn't. Finally, solutions do not have to be perfect. The fix I submitted isn't complete. There are obviously a few issues with it regarding responsibility, structure, and some other factors that weren't considered. We can even wrap up this video using this Google maintainer's response. Quote, I agree that the estimates are not good in general and we need more ways to control them. Your PR looks reasonably good, but we'll have to consider if we want to expose this interface. Yes, it would allow you to work around your current issues with some manual experimentation and configuration, but we would not want all users to have that. So that was a long video, but hopefully you learned a lot. And let me know what you think in the comments down below. And please give me a like and follow and subscribe. Thanks. Bye.